Assalamu alaikum. In this series of videos, we are going to talk about Chapter 8, Electromagnetic Induction, which is the first chapter of the second unit, Electricity. At the end of this chapter, we are going to be able to determine the magnetic flux, define the phenomenon of electromagnetic induction, state and apply Lenz's law and Faraday's law, apply Ohm's law across a coil, and explain the power distribution of a coil magnet system. In this video, we are going to explain the first objective, determination of magnetic flux. First, let's talk about the magnetic field. It is a region of space where a magnetic needle is subjected to a magnetic force. The magnetic field can be created by a magnet or it can be created by an electric current. The magnetic field at any point is characterized by its magnetic field vector B. The line of action of this field is along the line taken by the magnetic needle placed at this point, and the magnitude is measured by a device called Tesla meter. The unit of the magnitude of the magnetic field is Tesla. You must note that the magnetic field vector B is tangent to the field lines. Let's start with the magnetic field created by a magnet. In the case of a bar magnet, the magnetic field lines pass through the magnet from S to N inside the magnet. The magnitude of the magnetic field decreases as you move away from the magnet, while a U-shaped magnet creates a uniform magnetic field between its poles. Since the field lines are parallel and of same magnitude and direction at any instant, we must note that the magnitude of a uniform magnetic field is not necessarily constant. It may vary with time, but will always be equal at any point inside this field. In order to show that the magnetic field can be created by an electric current, let's take a look at Ørsted's experiment. An electric wire is placed above the compass parallel to it. We connect the wire to the battery. When the circuit is closed, we observe that the needle deviates to a certain direction. We can deduce that the current traversing the wire generates a magnetic field. Note that when we reverse the poles of the battery, the needle changes its direction. As a conclusion, Ørsted's experiment shows that the magnetic field can be created by an electric current. Now let's remember how a magnetic field can be created by an electric current. In the case of long rectilinear wire, the magnetic field created at a point M around this wire have a line of action perpendicular to the plane formed by point M and the wire, while its direction is determined by using right-hand rule. In this figure, the thumb finger takes the direction of the current inside the wire, while the other fingers or the curved fingers takes the direction of the magnetic field. The magnitude of this magnetic field at point M is equal to mu I over 2 pi d, where I is the current in ampere, mu is the permeability of the medium. If the medium is vacuum or air, mu equal to mu 0 equal to 4 pi times 10 to the power minus 7 as a unit. So B will be expressed as 2 times 10 power minus 7 I over d, where d is the distance from the wire in meter. In the case of flat coil of radius r and n loops, the magnetic field created at the center of this loop have a line of action perpendicular to the plane of the loop, and also the direction is indicated using the right-hand rule. But in this case, the thumb indicates the direction of B, while the curved fingers takes the direction of the current inside this coil. The magnitude in vacuum or in air is equal to mu 0 and I over 2R, where I is the current in ampere, mu 0 is the permeability in vacuum or in air, R is the radius of the coil in meter, and N is the number of loops inside this coil. Now in the case of solenoid of length L and N loops, the line of action of this magnetic field created inside this solenoid is along the axis of the solenoid. Its direction indicated using the right hand rule. Also, the thumb finger indicates the direction of the magnetic field, while the curved finger takes the direction of the current across the solenoid. The magnitude inside the solenoid is uniform and of magnitude P equal mu0 and I over L, where I is the current in ampere, mu0 is the permeability in vacuum or air, and L is the length of the solenoid in meter. Another important subject to remember is electromagnetic force, which is a fundamental force associated with electric and magnetic fields. To explain this, consider a conductor of length L, this conductor carrying a current I. When the conductor placed in a uniform external magnetic field, it will be subjected to an electromagnetic force F. The point of application of this force is the midpoint of the part of the wire subjected to B, while its line of action is perpendicular to the plane formed by B and L. Note that F is perpendicular to B and F is perpendicular to L. So F is perpendicular to the plane formed by B and L. The direction of the Laplace's force or electromagnetic force is determined by using right hand rule. In this case, the thumb takes the direction of the current and the index finger takes the direction of the magnetic field, while the middle finger takes the direction of the force. The magnitude of this force is equal to the absolute value of the current multiplied by the magnitude of the magnetic field and the length of the conductor subjected to this force multiplied by sine alpha. Now let's talk about the magnetic flux. By definition, the magnetic flux crossing a surface is the measure of the strength of the magnetic field crossing this surface normally. It is defined as the number of magnetic field lines that passes through a given surface area. The magnetic flux is represented by the Greek letter phi, and in SI unit, the unit of flux is Weber. Let's see now how we can determine the normal unit vector n. We choose around the surface a positive sense. The normal unit vector is perpendicular to that surface. Its direction is determined by the right hand rule. The curved fingers indicate the positive sense and the thumb indicates the direction of n. Note that when the positive direction is reversed, the direction of the normal unit vector n will reverse too. Now back to the magnetic flux, its expression is equal to flux equal ns multiplying by b vector dot n vector, which is equal to n times b times s times cosine angle between b vector and n vector, which is equal to n bs cosine alpha, where alpha is the angle between the normal unit vector n and the magnetic field vector b. B is the magnitude of the uniform magnetic field expressed in Tesla. S is the area of the loop whose SI unit is meter square, and n is the unit vector perpendicular to the plane of this loop. Note that flux is an algebraic physical quantity depending on the direction of n. If the angle between the normal and the magnetic field B is between 0 and 90 degrees, then cosine theta will be positive and then flux will be positive. While if the angle between B and the normal unit vector theta is between 90 and 180 degrees, cosine theta will be negative and so flux will be negative too. If the angle between B and normal is 90 degrees, flux will be equal to 0 since theta will be equal to plus or minus 90 degrees and cosine theta in this case is equal to 0. Now let's solve application 1. A circular loop of radius r equal 10 cm placed in a uniform magnetic field B. The magnitude of this field is equal to 0.2 Tesla, and this field vector is making an angle 30 degrees with the face of the loop or with the plane of the surface. Note that this angle is not between the normal and the between the normal and the magnetic field vector B. The angle between the normal and the magnetic field vector B is equal to 90 minus 30, which is equal to 60 degrees. The first question, calculate the magnetic flux through the loop. The expected answer is flux equal n bs cosine the angle between B and n, or nbs cosine alpha. N is equal to 1 since we have a circular loop of one turn. The magnitude of the magnetic field is equal to 0.2 times the surface of this circle is pi r square, so pi times 0.1 squared. Of course, the radius is 10 centimeter. We multiply it by 10 power minus 2 in order to convert from centimeter to meter. And finally multiplying it by cosine 60, which is the angle between the normal and the magnetic field vector B. The answer will be pi times 10 to the power minus 3 Weber. Another application to be solved is a solenoid of 1000 turns, each of surface area S equal 30 cm squared, is placed in a uniform magnetic field of magnitude B equal 2 times 10 to the power minus 5 Tesla. The solenoid is held so that its axis is parallel to B. Calculate the magnetic flux through the solenoid. The magnetic flux is equal to nbs cosine the angle between B and N. The number of turns is 1000. The magnetic field is equal, or the magnitude of the magnetic field is equal to 2 times 10 to the power minus 5 Tesla, and the surface of this solenoid is equal to 30 times 10 to the power minus 4 meters squared times 1, since the angle between the normal and the magnetic field vector is 0 degree. The answer will be 6 times 10 to the power minus 5 Weber. Now let's remember that the magnitude of the magnetic field created by a rectilinear wire is expressed by B equal 2 times 10 to the power minus 7 I over D, and the magnitude of the field created by a flat coil traversed by a current is B equal mu 0 and I over 2R, and that of the magnetic field created by a solenoid traversed by current I is B equal mu 0 and I over L. And the electromagnetic force or Laplace's force is expressed by F equal IBL sine alpha. And finally, the magnetic flux phi of number of turns N is expressed by flux equal NBS cosine angle between B vector and N vector. This is the end of part 1. Thank you for your listen.